Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and I'm here with Victor to dive deeper into the world of distributed hash tables. Before we begin, we'd love to hear from you. If you're enjoying our podcast, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you.
That's right, Sheila. Your feedback means the world to us. Now let's get back to our journey through DHTs. We're currently in Chapter 3, and today we'll be focusing on a crucial operation in DHTs, the put operation.
Exactly, Victor. But before we dive in, I have a quiz question for our listeners. Are you ready?
I'm always ready for a good brain teaser, Sheila. Let's hear it.
All right, here goes. In a distributed hash table with 1,000 nodes, if you want to store a file with the key myfile.txt, how many nodes will typically be responsible for storing this file?
Oh, that's an intriguing question, Sheila. It really makes you think about how data is distributed across a DHT. I'm sure our listeners are pondering whether it's just one node, all 1,000 nodes, or something in between. It's a great way to get us thinking about the put operation and data replication in DHTs.
Indeed, Victor. Now, let's start by refreshing our memory. Can you give us a quick recap of what a DHT is and what we mean by operations in this context?
Certainly, a distributed hash table, or DHT, is a decentralized system for storing and retrieving data. It's like a giant distributed key-value store spread across multiple nodes in a network. When we talk about operations in DHTs, we're referring to the fundamental actions we can perform, such as putting data into the DHT or getting data out of it.
That's a great explanation, Victor. So let's focus on the put operation. What exactly is it, and why is it important?
The put operation is essentially how we add or update data in a DHT. It's the process of storing a key-value pair in the distributed system. The importance of the put operation lies in its role in distributing data across the network, ensuring redundancy, and making the data retrievable later.
I see. So, if I understand correctly, when we perform a put operation, we're not just storing data in one place, but potentially across multiple nodes in the network.
That's exactly right, Sheila. In fact, this touches on our quiz question. Typically, a DHT will store data on multiple nodes for redundancy and fault tolerance. The exact number depends on the DHT's replication factor, but it's usually a small subset of the total nodes, not just one and not all of them.
Interesting. Can you walk us through the steps of a put operation? What happens behind the scenes when we try to store data in a DHT?
Absolutely. Let's break it down. 1. First, the client hashes the key of the data they want to store. This hash determines which node in the DHT will be responsible for the data. 2. The client then sends a put request to any node in the DHT. Point 3. This node uses the DHT's routing algorithm to forward the request to the appropriate node based on the key's hash. Point 4. The responsible node is receive the key value pair and store it locally. 5. Depending on the DHT's replication strategy, the data might also be copied to several neighboring nodes for redundancy. Point 6. Finally, an acknowledgement is sent back to the client, confirming that the data has been stored.
That's fascinating, Victor. It sounds like there's a lot going on behind the scenes. Are there any challenges or considerations we should be aware of when implementing a put operation?
Absolutely, Sheila. One major challenge is ensuring consistency across replicas. If we're storing the data on multiple nodes, we need to make sure they all have the same, up-to-date information. Another consideration is handling node failures or network partitions during a put operation. What happens if a node goes offline while we're trying to store data on it? Lastly, we need to think about load balancing. If certain keys are more popular than others, we don't want a small number of nodes handling a disproportionate amount of the network's traffic.
Those are great points, Victor. It reminds me of a distributed bookshelf system in a library. Imagine if we had to store books across multiple libraries in a city, making sure each book is in the right place, and that we have backup copies in case one library has an issue. Does that analogy work?
That's an excellent analogy, Sheila. It captures the distributed nature of DHTs perfectly. The put operation would be like adding a new book to this system. You'd decide which libraries should store copies based on the book's title, our key, ensure each library updates its catalog, consistency, and make sure you're not overloading any single library with too many books. Load balancing.
I'm glad the analogy works. Now, I'm curious about how the put operation in DHTs compares to insert operations in traditional databases. Are there any significant differences?
That's a great question, Sheila. The main difference is the distributed nature of DHTs. In a traditional database, when you insert data, it typically goes to a single known location. With DHTs, the data could end up on any of several nodes, and the system needs to be able to efficiently route both put and get requests to the right place. Also, traditional databases often use complex indexing structures to optimize data retrieval. DHTs, on the other hand, rely on their distributed nature and clever key hashing to achieve efficient data access without centralized indexes.
I see. So, DHTs trade some of the optimizations of centralized systems for the benefits of decentralization and distribution. Are there any common pitfalls or misunderstandings about the put operation that developers should be aware of?
Absolutely, Sheila. One common misunderstanding is assuming that data is immediately available everywhere after a put operation. In reality, there might be a delay as the data propagates to all replicas. Another pitfall is not considering the impact of the key choice on data distribution. If keys aren't chosen carefully, you might end up with hotspots in your DHT where certain nodes are overloaded. Lastly, some developers might overlook the importance of handling failure cases. Always assume that a put operation could fail and design your system to handle and recover from these failures gracefully.
Those are valuable insights, Victor. Before we wrap up, do you have any best practices or tips for implementing put operations in DHTs?
Certainly. Here are a few key tips. Point 1. Use consistent hashing for key distribution to minimize disruption when nodes join or leave the network. Consistent hashing is a technique that helps balance the load across nodes more evenly. Point 2. Implement retry mechanisms for failed put operations. Point 3. Consider using tunable consistency levels, allowing clients to choose between faster writes and stronger consistency guarantees. 4. Monitor the distribution of your data regularly to detect and address any hotspots. Point 5. Use appropriate timeout values to balance between giving operations enough time to complete and not hanging indefinitely if there are issues.
Thank you, Victor. Those are really helpful tips. Now I think it's time to reveal the answer to our quiz question. In a typical DHT with 1,000 nodes, how many nodes would be responsible for storing a file with the key myfile.txt?
Great question, Sheila. The answer is that it depends on the specific DHT implementation, but typically it would be a small subset of nodes, often around 3 to 5. This replication factor balances between having enough redundancy for fault tolerance and not overwhelming the network with too many copies of each piece of data.
Excellent. To summarize today's episode, point 1. The put operation is fundamental to storing data in DHTs. Point 2. It involves hashing the key, routing the request, and storing the data on multiple nodes. 3. Challenges include maintaining consistency, handling failures, and load balancing. 4. DHTs differ from traditional databases in their distributed nature and routing mechanisms. 5. Best practices include using consistent hashing, implementing retry mechanisms, and monitoring data distribution. Thank you all for listening. If you enjoyed this episode, please visit crashcasts.com and consider joining our Discord community. Your support on Patreon helps us continue creating this content. Don't forget to subscribe and rate our podcast. Until next time, happy coding.